la conferencia que ofreció a principios del año, en febrero más o menos. Pero esta es un poquito continuación de. Espero que les guste bastante y lo aprovechen. Me han pedido unas recomendaciones. Por favor, pues en respeto al doctor Vigder, que pues ha venido desde Canadá para ofrecernos las pláticas, pues que le pongan atención. Si hay algún problema con disciplina o algo así, va a haber gente que los va a escoltar fuera del auditorio. Arquitecto de sistemas de control en los laboratorios nacionales de Canadá. Tiene bastante experiencia en sistemas de control y en software, temas. Y entonces, pues creo que esta charla les va a interesar bastante amena. Yo los dejo con él para pasar más.
Turn off that one. Get too much back. Okay. Hopefully everything is working here. I apologize somewhat for having to speak English. My Spanish used to be good many years ago, but that was many years ago, and I don't feel qualified to give this lecture in Spanish. I have a feeling you'll understand me a lot better if I speak English. Yeah, this is wonderful being here, and I've been in Guatemala now and at the university for about the last 2-3 months since January, working with Professor Luis Furlan. Luis and I go back a long ways, as I was here 40 years ago as a teacher at this university, and then went back to Canada and sort of built my career there. And now my career in Canada is coming to an end. I decided to come back here to the university, Universidad del Valle, for a while to just reacquaint and get away from the Canadian winters. I unfortunately head back next week. Notice this week the temperatures actually got above zero in Canada, and I think there's still over 1 meter of snow on the ground, so it's going to be pretty miserable when I get back there for a little while yet. But yeah, so I'm glad I'm able to give this lecture, and I hope I can inform you about a few things. So I titled this lecture, Do I Really Know Anything About Software Engineering and What's My Grade? And sort of the concept that I have for this talk is that I've spent 40 years now in software engineering and computer systems. I've been a researcher, I've been a teacher, and I've been a practitioner where I actually built software systems. What I decided to do was sort of, first of all, start by putting on my teacher hat and my researcher hat. And the thing about teachers and researchers, they know how to do everything, but they don't actually do anything. So I start and say, well, here's how you're supposed to do it. Here's how software engineering is supposed to work. And you sort of go in a nice sort of orderly flow to develop your system. I then sort of switch hats and put on my practitioner's hat, looking at the projects that I have actually worked in and developed. And here's what we did. And it never goes according to plan, of course, and it's chaos, and it's, you know, you're under pressure, you're under deadlines, and things don't work all that well. But, you know, you get the system out eventually. And then I go back, put on my teacher hat, and give myself a grade. What did I do? Get an A, get a B, get an F. So to just see how I did relative to sort of the theory of how software engineering is supposed to work versus the practice of what I actually did when I was working with teams where we tried to build software systems. So I'll try to sort of go through that. You're going to use a different software engineering process depending on the kinds of systems you're working on. So I just want to give you an idea of the kinds of systems I was working on. They were software intensive projects, so we did a little bit of hardware development in some of these projects. And I'm not talking about it. When I talk, I'm not going to talk about one single project. I'm going to be talking about, it's really a compendium of a lot of different projects that I've worked on that I've just sort of amalgamated some of the concepts. In this case, the developers and the users, i.e. myself as one of the developers, and the people that were going to use the software are part of the same organization. So we weren't like developing an app where we were going to push it out to 100,000 users who we didn't know who they were, or we weren't selling a product, or we weren't providing a web application where the users sign on and we don't know them. We're all part of the same organization, so they were in the same building or the same team, or so I was able to interact with them quite a bit. Our team size at any one time, again, we're not talking about hundreds of people on a team, talking about anywhere from 2 to 5 people, maybe 5 or 6 developers on the project working on it. Projects might go on for multiple years, so people would come in and out. So you might have 10 or 15 different people in total that worked on the project. But at any one time, we probably never had more than 2 to 5 people. Developers geographically distributed. We weren't all in the same building, in the same office. Could be in different buildings, different cities. But we somehow had to communicate with each other for the development. And we had a single deployment or a small number of deployments. And what I mean by that is we weren't just building one system that ran on one computer. We might have 15 or 20 or 30 users of the system, and they each had their separate deployment of the system that were installed on their computers or on a set of computers that they used. So we just didn't have one computer running one software. Might have had one software system, but it would be deployed at 20 or 30 sites where it was being used. So it gives you some idea of the kinds of systems I was looking at. And then there's all kinds of software engineering activities, and I'm not going to cover all of them in this. I'm going to skim over a number, but the ones I'm actually going to try to look at how I did on my projects that I was working on. I'm going to look at the overall software engineering process. What's the steps we went through in developing the software. Requirements engineering, how we determined what it was we were going to build. The software architecture, which is the high-level perspective or high-level design of the system, how it's structured. How we went about testing the software and the system. I'll talk a little bit about how we did that whole build, integrate, deploy activities. And finally, I'll get to the really exciting topic of the documentation, which everybody loves to do, I know. Okay, the software engineering process. So this is sort of the theory part. This is how it's supposed to work and how the textbooks tell you it works. I have some references at the end of where I got it. SOM, that's sort of the Somerville textbook. I've used a couple of textbooks like Somerville and Pressman for getting this information. But say there's different models one can use when developing software. One of the first you always see is what they always call the waterfall model. I don't know if you've taken a software engineering course, they usually put that one up as the first model you use and then tell you why it doesn't work and why nobody uses it. I put it up there, actually, I guess we talk about it as almost like a straw man, as we say in English. I don't know if you use that term in Spanish, hombre de paja, it has the same meaning, but a straw man is a false argument you put up so you could immediately tear it down. So this is sort of the straw man here, the waterfall model, the idea that when you develop a software system, you go through the requirements to determine what you're going to build. You try to go through the design, and again, you fall down into the actual implementation of it, the verification that you built the right system, and then it goes into maintenance mode, and everything follows nicely through this waterfall down to the bottom here, step after step. That probably works not too badly if you're building a bridge or building an office building, but it doesn't work very well in software systems. I think they started waterfall, they defined that as the software standard. At one point, I guess back in the 1970s and the 1980s, the US Department of Defense decided that we had to use that model, and they wrote pages and pages of documentation about how you're supposed to do it. And of course, whenever they tried to build anything, it failed. So after about 10 or 15 years, they threw away that whole model and then came up with a different model of how to do it. So the next model that's mentioned in the Somerville, he talks about the incremental model of software development. And in this model here, these sort of ovals represent the activities and the squares represent the outputs. And in this model, you basically just provide a very basic outline description of what you're going to build. And then you go into the activities of specify what you're going to build, you develop, do some development, and you do some validation that you built the right thing. And you just go back and forth between these activities, up and down, generally outputting various versions of your system until you have a version that works and you're in maintenance mode and you just come out with new versions. Other model that they have sometime is the agile, where you plan, build, launch, and you get feedback then on what build was right and just keep going around this loop here. Depending on how you're doing your agile, this can be very quick, sometimes 24-hour turnaround time for going through a loop like this. But again, it's just a different model over the waterfall of how you develop software. So what did we actually do? And when I put this on the board, I don't want to give the impression that we sat down and sort of planned out our software engineering process at the beginning of a project. Did not do that. Generally, what we did is we had some interaction with the users, find some need to build a system, and then we would start working on the system. And as it grew, we simply developed the process on the fly. So as people came in and we had to apply more process to our development, we simply applied a little more rigor to what we were doing and came up with a process. And what I'm showing on the board here is actually, this talk was interesting for me to prepare because I could sit down and say, what did I do to get this system working? Because in some sense, what you're seeing is my retrospective, looking in the rearview mirror at what I did, rather than sort of, did not plan all of this out. It's just as we needed to sort of introduce a process, we would introduce the process as we just started to realize that there were problems and how people were interacting. So I would say what we did is, first of all, we did very similar to what we had in the iterative. We simply got together and figured out a basic outline of the requirements that we needed. We planned that out as to what we were going to do. We do some implementation. We develop a prototype or deploy it. And when I say a prototype, sometimes we didn't have a full working system. But I always thought it was important to get a system out to the users or show them progress as fast as possible. What you don't want to do is go off into the back rooms for 2 years, then come out with a system and show it to the users. You have to show progress to the users all the time. Even if it's not a fully working system, you have to show the progress. So we develop either prototypes or working systems and deploy them. Something we could show to the users and get feedback. And then we just sort of go through a loop like this until so the system would evolve. And if you look at that, that's very similar to what we have sort of at this point, I would say, is similar to what we did in most of the projects I was working at. I also don't want to give the impression that these are well-defined activities in our process. We tended to be doing all of these somewhat concurrently. Because we were doing systems that weren't, say, safety critical, we could be pretty loose on our process. You're doing something like an avionics system where, when it fails, the plane goes down. You're going to be a little more formal in what you do. So if I was looking at the grade I'd give myself, the positives about our process, I think it was very lightweight with limited overhead, which is sort of what you want to do if it's not a safety critical system, if you have 4 or 5 people working on the project. We had lots of interaction with the user, was, I thought, very important. We could develop the prototypes, and our versions were developed relatively quickly. And we had a quick turnaround with new versions. Negatives, there was no formality. It was somewhat disorganized. As I said, we were sort of in all of those activities concurrently, and it wasn't necessarily probably the best process. There was no way to measure and improve the process that we had. I mean, that becomes much more important when you're in a big organization with many developers, where you want to understand how fast are we getting out new versions, how fast are we fixing the bugs, what's the productivity of the people. We had no way of really measuring or improving that. And I said new versions were a little too easy to create, suffer from versionitis. It was at times a little difficult in our process because we were looping around there so fast. We'd end up with a lot of versions coming out, and keeping track of what versions we had of the software and where they were deployed and what was going on was often a very difficult thing to do. So what's my grade? Overall, I'd give myself a B+. I think we did a pretty good job. Certainly wasn't an A, but a B+ is not a bad mark, I think. So I'll say we got a B+. Besides, I'm grading myself. I can give myself whatever I feel like. Next thing I'll talk about a little bit is how we did our requirements engineering. I always say there's two questions you're trying to answer when you do your requirements engineering. First is, what are we building? And the second is, why are we building it? Okay. The requirements engineering is trying to get the requirements, figure out exactly what you're going to build before you go ahead and build it, or often while you're building it if it's your incremental model. So you have to decide what are you building, and I also say, why are you building it? I have a couple of other diagrams, models I got from the Somerville textbook about requirements engineering and how it should be done. And again, he's got one model where, again, these ovals represent activities, squares represent the outputs, and says, okay, you do a feasibility study first to make sure what's possible to even build what you want to build. Some have to elicit and analyze the requirements. You then have to put those requirements in a formal specification. Your formal specification can be anything from just a Microsoft Word document to a spreadsheet to a mathematical formalism of the specifications. And finally, you have to do some sort of validation of your requirements to make sure you're building the right thing, and this is what the users actually want and actually use. So that's sort of one model. It's sort of got that waterfall look to it. Another model, it comes from the same textbook of how you do requirements engineering, is basically he looks at two sources of information for the requirements. First source is the user. Okay, user obviously has some activities they have to do. They have to use the system. They have to know what they're doing. So you have to get requirements from the user. But also there's this idea of the problem domain as input to the requirements engineering process. And that's sort of not explicit down in this model here, but I always thought understanding the problem domain, I thought, is always one of the most important things in trying to do requirements engineering. And what I mean in understanding the problem domain is if you're building, say, order processing system for a business, you have to understand not just order processing, you have to understand business. You have to understand how the business operates. You have to understand its warehousing, inventory, its accounts receivable, accounts payable, finance, all of that. So you have to understand the large problem in order to build the little small part that you want to build. I tended to work in the scientific and engineering domain, and whenever I was doing, say, in the science domain, I always tried to understand the science that I was working with. How do they do the science? How do they run the experiments? What's the physics or the chemistry that's involved in the science before I actually tried to build a little piece of software that the scientists were going to use. And in this model, so you have the inputs from the user, inputs from the problem domain. So you have to somehow elicit from these, you extract, try to understand what the requirements are. You need some sort of specification of the requirements. Again, anything from an informal text document to a formal mathematical specification. And you need some way of validating those requirements, usually with the user, with the organization that you're working with. Okay, so there's a theory of requirements engineering. I tried to come up with this diagram of how I think we did it, and it's probably a little more complex, the diagram, than what we actually did. I don't think what we did is nearly as complex as the diagram, but this is what I came up with. So starting over here, if I looked at the user input, that's what I'm talking about here. Interviews with the users, observation of the users, just spent some time with the users to see what they were doing and to formally interview them about what they were doing to try to understand what they thought they needed. This isn't always what they need, of course. And the other thing I always did was some domain research. Again, looking at the science of it, looking at the engineering, looking at the business that was going on to try to understand that. And from that, you could extract certain domain knowledge, functional requirements as to what the system was supposed to, how it was supposed to work or what it was supposed to do, and the non-functional requirements, anything from security to performance to all those. Once we had that, then we could sort of go through this loop, which looks a lot like my software engineering loop. We could develop the prototypes and deploy them and get the feedback and the planning. And through these prototypes and interaction with the users, we could sort of extract more of the requirements. Tools I used, I tried to look at the software tools I used. We didn't really use many tools for doing this. Shared documents up on wikis, we'd be able to put our notes, put our information up on shared wikis and communicate back and forth that way. Writing information on whiteboards, we had a lot of stuff that just went on whiteboards, little boxes and arrows sort of showing how things worked. And GUI frameworks, GUI graphical user interfaces, so the widgets, the buttons, the text boxes. We used those kinds of frameworks to quickly put up prototypes, particularly when we were doing this prototyping, so we could show to users, how things worked. So that's really how we did the requirements. Positives about that? I think we obtained a good understanding of both the domain and the functional and non-functional requirements that the users required. Most of the systems I worked on, we seem to be reasonably successful in keeping users happy. Never keep all your users happy, but if you can keep most of them happy, that's pretty good. Users felt involved in the process. We made sure that we were continuously talking to users and showing them things and asking them questions. And again, that was important for getting a successful system because the users felt that they were part of the development. And I think in general, for most of the projects I worked on, the things they needed, we got that right. They seemed to be relatively successful for most of the projects. Wouldn't quite say 100%, but for almost all of them, I think we did pretty well. Negatives, there were quite a few implemented features that never got used, which would lead me to believe that when we tried to understand the requirements, sometimes we missed and put in features that weren't really needed. Spent a lot of work on some of those features and they never got used. So kind of a waste of time, but I don't know if there was a way of filtering those out before we went to the effort of implementing them, but that was part of the problem we had. There was no written record of the requirements and no record of the motivation for the requirements. I go back a couple of slides. They always talk here about eliciting the requirements from the users in the problem domain, specification of the requirements in some sort of written form, and then the validation. I think I did pretty well on the validation and the elicitation, but we never really had that formal documents, those spreadsheets, those mathematical formulas, those, that really describe what we were going to build and why. Had a lot of stuff on the whiteboard, but over time that tends to get erased. So, I mean, that was sort of one thing that I didn't think we did all that well on, but, you know, in the end of the day, we did pretty well. So if I say, what mark did I get on this? C. Okay. I think I'm going to complain to the teacher about that mark because I think I did better than a C. That's too low. I'm going to put in an appeal for that because I think I can do better. Okay. So, but, you know, not too bad. Software architecture. Okay, that's one of those terms I hear a lot of people spend a lot of time trying to define what do they mean by software architecture and what is architecture. I've even spent time arguing this myself, and it's what's the difference between architecture and design. And so I went to a couple of sources to try to figure out what software architecture was. First one is sort of the fount of all knowledge, Wikipedia, where you start all your searches. Software architecture refers to the high-level structures of a software system and the discipline of creating such structures, systems. Okay, so I asked myself, well, what does that mean? I said, I don't really know what that means. Doesn't mean all that much to me. So I started looking for another definition. And I got, this is the IEEE definition. Architecture is the fundamental organization of a system, embodied in its components, their relationships to each other and the environment, principles guiding its design and evolution. This made a little more sense to me. Once you start talking about the components and the relationships, my original formal training is as a mathematician, and I read components, relationships, organization. That's starting to sound like an algebra to me, and I can sort of begin to understand, okay, algebras, I understand. So then I started looking at, well, how people characterize architectures and define them. And again, you get this explosion of all kinds of terms and perspectives. They talk about Blackboard and client server and microservices and service-oriented and data-centric. And again, I said, I can't make any order of this. I got to come up with something and more coherent that I understand. Since I'm giving the talk, I can come up with anything I want to come up with. Joy of giving these talks and being the teacher as opposed to being the student. And I sort of followed along with the IEEE. The architecture somehow involves entities and their relationships. I'm not going to define what entities are at this point. It can be different things depending on the architecture perspective that you want to be looking at. But it's oftentimes architecture seems to be driven by the non-functional requirements, not so much as to the specific functions that it's going to perform, but things like what sort of performance levels do you have to achieve? What about security? What about fault tolerance? All those sort of those requirements that are really nothing to do with the function of the system, but are important. And it sort of seems that those often drive this high-level entity relationships that you start talking about when you try to meet those. And the other thing is it's difficult to modify or change your architecture once you've settled on it. When you talk about more detailed design, if you have a software object or a software module, it's relatively easy to change that. You know, it might take you a few weeks of coding, but you can sort of pull out a couple of modules, rewrite them, and insert them back into the system. But your architecture tends to be more set in stone. And when I looked at the systems I was working on, I tended, the non-functional requirements that tended to drive the architecture, I thought were what I would call maintainability and reliability. I won't sort of go into detail what I mean by those terms. Other than maintainability, I was sort of always looking at how do I keep a software system maintained for many years, given that it's being maintained by a small group of people who keep changing over time, so you don't have continuity necessarily in the people working on it. And has to evolve, bugs have to get fixed, features have to get added, and reliability in that you wanted something that works, if not 24/7, close as you can get it, you don't want a lot of downtime. So that's sort of the theory of architecture. In terms of the practice of architecture, I wasn't, the projects I've been working on, I wasn't quite sure sort of how to approach this. What I thought I would do is sort of just look at what I would define as some of these elements of the software architectures of the systems I was working on. And just when you talk about real architecture, where when you're designing a building, you have different perspectives. You might have one perspective that gives the outside view, a perspective that gives all the mechanical and electrical, a perspective that gives the various load-bearing walls and such. You have different perspectives in software architecture of a system. So for example, one of the systems I worked on, this was what I would call the network architecture that we had. The system we built is down here with a number of computers and pieces of equipment on it, all connected over a local network with its own sort of database. That was completely isolated, ran completely separately from the corporate network. So for, here the corporate network would be your, I guess you have a uvg.eu.gt network. So that would be like the corporate network. And then that as a gateway to the general internet. So this network architecture would allow remote access to come into the local network, but it also had the advantage that we were completely isolated from the corporate network. So if the corporate network went down or had some performance issues, you might lose your remote access, but this system would continue working as is. Now, probably not a problem here. Here, the UVG network never has performance issues or ever goes down, so you don't have to worry about that. The organizations I worked at, we always had problems with our network, so this sort of provided us with that kind of buffer. So that's what I would call our network architecture. Use something what I would call an event-based architecture as well. This is, again, the architecture from a different perspective. So we had remember we're talking, when we looked at our definition of components of architecture, it was entities and relationships were sort of the key aspects. Our entities here, I just call components, which would generally be large-scale software programs. So they're not talking about a software object or a software module, more like a whole software program or a software system. And communicating through an event pool. If you're not familiar with that kind of architecture, basically these components sort of put events into the event pool without knowing what happens to those events, and other components pull events out of the event pool. It's sort of decoupled. So rather than something like a function call where you have a strong linking between these components, or pipes and filter, pipes where you have a strong linking between them, it simply decouples the components from each other. And that made it sort of very modular and easy to add and remove components. It also made it more fault tolerant, so components fail. The other ones can sort of still operate, perhaps with a degraded functionality. If I looked at my functional architecture, again, looking at the various components we had on our local network multiple computers, and we could assign components to various computers for any kind of reason, performance reason. But again, it was easy to move components around between computers. If computer 3 failed, we could take this component and move it over into another computer if need be. If an organization, perhaps some of the deployments could only afford one computer, we could put everything on one computer. It affects performance, it affects fault tolerance. But again, it's just one way of looking at the software architecture. So what do I give myself as a grade on my software architecture? Well, the positives was everything worked And I think it met most of the functional requirements and even most of the non-functional as well. Easy to reconfigure. I'd add in there that generally our architectures I thought were very simple. You know, it's easy to explain them to people. We didn't have a lot of complexity, I felt, in these architectures. We met most of the non-functional requirements, but there were some areas like performance and fault tolerance, which I didn't think we were as good as we probably could have been. So what do I give myself when I put on my teacher's hat? I gave myself a B-, and I thought we did reasonably well, but not perfectly. The fact we didn't meet all of our fault tolerance and performance that I would have liked to have seen wasn't perfect. Okay, testing. How did we do on the testing? Theory of testing, I took this as, and I use Somerville a lot, his textbook for this. I wasn't quite sure what to do in terms of theory, so I just looked at Somerville and it says, here's the kinds of when you do your testing. He talks about doing development testing while you're developing your system. Talks about test-driven development, which is actually an interesting concept, where before you actually do any development, you write your tests first, and then you do your development against your tests. So if you're building the system, you write all the system tests, and it almost becomes your requirements before you actually go and write your system. Or if you're down at the object model, before you write an object, write all the tests for the object first, and then you write the object. Talks about release testing. You know, before you actually release any software to a user, you always do release testing, any kinds of regression testing and integration testing. And then, of course, handing it over to the user for the user testing. So that's sort of what Somerville defines as when you test. He also has a diagram that shows how you test. And he talks about, again, these are the activities, the squares up top are the outputs. So he says, design your test cases. And this is where you go in and do everything from, say, okay, kind of test coverage do I want? Do I want to, you know, test every single line of code? Do I want to test every loop? Do I want to test every possible data input or every possible class of data input? So you define your test coverage and look at your test, on your test cases. Usually there's a lot of preparation of test data as well. A lot of work in putting that together, of making sure you got the proper inputs. And you run the program with your test data and you compare the results. Test cases have to define not only the inputs to the system, but your expected outputs, and you get a test reports. Now, there's always a couple of problems testing. Problem number one is it's a hell of a lot of work, like a hell of a lot of work. And unfortunately, a lot of management doesn't understand that. If you have a management who's really understands software engineering, they know how much work testing is. But if you have a management that doesn't have training in software engineering, they just don't understand that you can easily spend 50 or 60% of your time going through these processes of testing. There's always the pressure to get it out and get it out and get it out. Testing is one of the areas that you usually cut back on. That's one problem. It's just so much work to do the testing. Second problem I find with testing is that most developers hate doing it. They just want to write the code, get it out there. You don't have to test it, it just works. So it involves a lot of discipline on the software developer's part and on the manager's part to motivate the software developers to do the testing. So what sort of testing did we do? Well, we did sort of, in a more formal sense, a couple of kinds of tests that we did. We did some what's referred to as unit testing, and this tends to be testing in the small, like testing usually an individual software module. Sometimes even down to the level of an object, but usually a module containing a number of objects. And we'd have our unit under test. And then what you would do is you'd have to create your entire test harness for doing this. So you have your unit under test. You have all the other components in the system that your unit under test is going to talk to. Some of those you've got written already when you do this testing this unit. Some of them you don't. They're not written yet. There's other units that interact with this one. Then you have to simulate them somehow. You're often testing to an outside environment that can't test in a real environment. I say if you're building an avionics system, you can't test your software by putting it in the plane and flying the plane. Then you have to simulate a plane flight. So you have to simulate. There's a lot of simulation that has to be developed and written to actually do this testing. You have to do your test suite, which describes all the test cases, all the inputs, and all the expected outputs for each test case. And I put the tool we used here because most of my work was done in Python. So I used a tool called PyUnit to do the testing. All the other languages, Java and C, they've got similar tools as well. And this is these tools are kind of handy because they could look at your test suite, pull out all the test cases, drive the unit under test, compare it to the results, and print the report. So that's sort of what we did in terms of our unit testing. I say putting this together, doing this test suite, well, look, doing this test suite, doing these simulated components, put together this test harness, that actually takes quite a bit of work to do. So put a fair amount of effort into that, do this unit testing. So we did some unit testing. We did some GUI testing, the graphical user interface, which is very similar. The main difference here is you don't have a standard PyUnit or JUnit kind of tool here to actually run your test cases and drive your GUI. So we actually had to write this kind of a test driver, which would simulate moving a mouse and the mouse clicks and keyboard typing that a user would put in there. And again, that was a lot of work. And because we don't have a PyUnit or a JUnit or one of those, we had to sort of come up with our own format for test scripts. And the GUI test driver would read the test scripts and drive the GUI and generate the report. So this was even more work than that previous slide because we had to design how we were going to format our test scripts, and we had to write this part ourselves here. So it really was a large effort to do this kind of graphical user interface testing. So what's the testing grade here? Positives, we had some, but not much, unit test coverage of modules. We had some user interface testing. Negatives, almost everything. We did some user testing, but that tended to be, try it out, it works, away we go. We didn't really have any integration testing or regression testing or beta testing or anything else testing. No formal analysis of our test coverage to make sure that we're, saying that we've covered all, possible paths through the code or all, different types of data inputs. So what grade do I give myself on this? This was actually the easiest one to grade of all the activities I was grading. And I don't think there's any doubt whatsoever as to what grade I would give myself for this one. It's an F. And I'm not even going to appeal that one because I absolutely agree. We got lucky with this one. Most of the systems I worked on, we never really had a really bad situation arise. But I would say that we were an F on that one. The build, integrate, deploy. This is sort of, I think, something that's sort of come to the forefront a little more recently in software engineering about how do you actually automate this whole build, integrate, and deploy process. I know the buzzword that seems to be going around a lot now is this concept of like these DevOps. How do you combine development and operations? You know, the build and the integrate. Well, the build is really part of the development, and the integrate and deploy is, in some sense, the operation. So how do you do this DevOps? And in terms of theory, again, it's sort of all over the map when you try to do any kind of Google search or look in the textbooks or about this. But I'll just sort of go over what they talk about a lot now, which is this continuous build, continuous integration, continuous deploy model. Continuous build is the idea that you have your developers, working on the system, and they each have their copy of the system, and every time they commit their changes, there's an automatic build, okay? So automatic build, it builds the entire system, automatically runs the tests, and you know what they did is correct. This assumes you have a really good testing framework in place too, which we never, of course, had. So that's sort of this continuous build, that every time a user do some development, they commit that change, automatic build, automatic test. Then you have this idea of the continuous integration, that normally you have sort of some central repository where you have your main versions of the system being maintained. So as soon as they build a new system, and as soon as they pass all the tests, it'll get integrated into this central repository, and the other people will also have their developers change this person makes that gets integrated in here will get reflected back and integrated in with these developers. This obviously has a huge advantage because you don't have these people sitting there for 3 or 4 or 6 months doing their development and then trying to integrate all their different work together. It's sort of happening on a continuous basis. So if there's some conflict in their work, you find it really quickly. You don't find it 6 months down the road and have to fix everything. And then, of course, there's this concept that I find quite amazing, this continuous deploy, which as soon as it gets integrated in and passes all the tests and runs properly, you push it out to all the users and the users start using it. I must admit I don't quite understand this concept. You're pushing out new deployments to the user every few days. I can't think of a easier way to get angry users than to do something like that. But it sort of gives you some idea of some of the modern thought is this continuous build, continuous integrate, continuous deploy. Okay, so that I put in as sort of the theory of build, integrate, deploy. What's the actual practical way we went around doing this? Well, again, I had a hard time actually coming up with this diagram that sort of describes what I think we did here and how we worked. But I gave it a try. It might make some sense to you. I don't know. We'll see. Basically, we start out up here with creating a new issue. An issue is something that has to be worked on, something that has to be done. A new function that has to be added, a bug that has to be fixed, a refactoring of the code that has to be done to reorganize the design a little bit, simplify it perhaps, something where performance is degrading, we have to do something to improve performance. So an issue gets raised. I put down the tools we use to do this. In this case, issue tracking and change management is sort of one of the most important things in any engineering work. And in software engineering, there's certain characteristics of it. And these are the tools we tended to use over the various projects I worked on, Mantis, Bugzilla, and Track. I assume that some of you have probably had some experience with issue tracking software, but it's a great tool for organizing a team because you can put the issue in, it keeps track of, how, and then put some triage on it to determine how important it is. It keeps track of discussions of the issues. It keeps track of who's working on it. You can plan out what version of the software you're going to implement this issue in. So we generate a new issue somehow or other. We'd assign that issue to somebody when it sort of was time to actually build or do something about the issue, fix the bug or add the function or whatever. Once that person it was assigned to, they could create their own branch to work on. And I won't go into great detail about version management systems. I assume many, if not all of you, had some experience in some version management, be it Subversion or Git or whatever. Those are the ones I tended to use, was Subversion, Git. These are probably the most important tools, the software engineering discipline, I would say, are these version management systems. They have saved me so many times in terms of being able to keep track of all the versions, what changes are being made, and who's doing what. So Git seems to be the one of choice now, and I always find Git to be I'm amazed at it. It's almost like magic to me what it can do. If you're not familiar with Git, it was actually written by Linus Torvalds, the writer of Linux. And he actually wrote it while he was doing Linux. He was using another version control system. And I guess he got into a bit of an argument with the people that developed that version control system. I guess some licensing issue. He didn't agree with the licensing issue, the way they had licensed their software. So he says, to hell with you, I'm just going to write my own. So he sat down and spent a few weeks writing Git, and then he just wrote it so he could continue writing the Linux operating system. And now Git is probably the most common one used now, certainly in open source projects. I think Git is a version control of choice, and in a lot of commercial projects as well. So in this case, what we'd use it, the user could create their own branch to work on. And the nice thing about branching, it keeps track of all the changes that are made, who's making them. They can make any changes they want and not impact the main system. And so they can develop on their own branch, the developers. Once they're happy with their development, they commit their work into their own branch. And the committing is a concept that's in most of these version control systems. They can go back and do some development and committing. And once they think the issue has been finished and is done, they go to who's ever controlling the master version. And the person doing the master version can sort of use these version control systems to see exactly what changes have been made, make sure all the tests have been run, assuming you have a good test cases that are all written down and specified. And if they're happy with that, they merge it into the master version. And again, these tools like Subversion and Git, they help you do those merges and help resolve all conflicts because people have done different things. And then we had a whole bunch of these shell scripts that we could use to deploy these versions out to our users automatically. So it wasn't quite continuous build, continuous integration, continuous deploy, but I'm not sure those concepts are the best, but I think we did pretty well. So what are the positives? We had good tracking of issues. I think we had pretty good version control. Our build and deploy were pretty much automated, not continuous, but they were automated. Easy to deploy and the multiple platforms. And we kept a log of all our deploys. So we could go back and say, well, what was deployed on this system 3 weeks ago? We had a log of all of that, so we could, something went wrong, we could always use our version control system, go back to a working version from a week ago or 3 weeks ago or a couple of months ago. Negatives, I wouldn't say there was much negatives. It sort of required a fair amount of discipline from the users. Oftentimes, creative software developers hate discipline, want to be creative. So there's kind of a certain amount of discipline you have to impose on either yourself or management has to impose on the people. But I think that's true anywhere. So overall, I think we did pretty well on that, so I gave myself an A. All right. Documentation theory. There isn't really a theory of documentation, but I came up with something anyway. If there's one thing that developers hate, more than testing, documentation. But they're both important. So I went in here, and this is from Wiki, when they talked about software, or Wikipedia, when they talk about software documentation. They look at the types of documentation that should be developed. They talk about requirements documentation, which I've already mentioned that we didn't really have any. Architecture and design documentation. Technical documentation of code, your algorithms, their APIs, and their end user documentation for end users of the system. Now, when I went to the practice of this, the question I generally ask about documentation is, what do you really need? What is important to have written down as documentation? Notice a lot of these systems, you'll have bookshelves full of documentation, most of which is never looked at. And I didn't want to waste time writing documentation that wasn't going to be looked at. So I tried to ask the question, what is it we needed? And I sort of came up with two kinds of documentation that was really important for most systems I worked on. One, you do need some kind of user documentation. You don't want to go overboard on the user documentation. If it's a well-built system, it should allow users to be able to explore, to figure out how the system works. So you don't have to document every single menu entry and every single button in the user interface. But you do need some sort of quick start guide, some sort of use cases about so if you're doing an order processing, how do I process an order from beginning to end? Or in the scientific software I was doing, how do you do an experiment from beginning to end? Just, go through the main highlights of it, enough to get the user started so that they can just explore and figure out what that button does and what that menu entry does. So it allows the user to explore. So this user documentation I considered important. Second kind of documentation I considered to be important was the document that would be required by the people maintaining the system. So I take it here, the manager, maintainer, the administrator, who's ever running the system and keeping it up and running, giving it a kick when it stops working and breaks down. And what I put there in the documentation was primarily the architectural views, because that gives you sort of the high-level perspective of how the system works. I never believed in doing a detailed documentation down at the code level. I mean, the code should be well structured, it should be well commented, but I never thought you needed sort of a detailed descriptions and documentation for each object, as long as it's, say, well commented and structured. But what you do need is a guide where to look in the code. So if somebody has to go in and change the code, describe in detail how the code works, but they know what they have to do. They know by looking at the architectural view and an overview of the code, it's probably in one of these modules, and then they can go look in the code to figure out what they have to do. So that's sort of the objective I had with the documentation. So I tried to sort of come up with a diagram of how we did the documentation. And again, I drew this diagram and I say, wow, that's pretty impressive. I didn't realize what I did was all that complicated. But here's how I sort of arranged the documentation for at least one of the projects I was working on. Documentation, this is the source of my documentation. So I didn't sit down and write a Microsoft Word document. I mean, there's nothing worse. You have this big Microsoft Word document. Where do you put it so that people can even find it? So there were sort of three sources of the documentation. There was sort of, in this case, in the Python code, I tried to have as much of the documentation right within the code as I could. So if I was describing some element of the user interface, I tried to put the documentation right in the code with the user interface. And I know, Python has this concept of doc strings, so you can embed documentation in the code. Most modern languages have a similar concept, be it Java or whatever, so there's a way of embedding documentation in the code. I also used a lot of these RST markup files. RST stands for restructured text. If you're familiar with HTML, this is sort of just a simplified markup language. I don't know if you use something like, there's Markdown that they use in Jupyter and and such. So there's various of these various simple markup languages where you don't have to go to full HTML to do your markup. So I'd have a number of those files, and I'd have a number of README files, usually within a single directory, that would describe what was in that directory, give an overview of what was in that directory. That was sort of where I actually put the documentation. I then used a tool called Sphinx, and again, there's lots of other tools that can do a similar kind of thing, and extract information from all of these files, goes through the Python code, it understands the Python syntax, so it can extract the documentation from there. RST markup files, I sort of point Sphinx to those files and to the README files, so it could extract those, and it could create a nice HTML document that's with all the links properly linked and all the references properly referenced and the downloads properly downloaded. Actually, it's, again, quite an amazing tool, I find. And I also put out a PDF document so that you could actually, if you really wanted to, print that out. When we did our deploys, this was part of our build. So when we did our deploys, these documents would actually get installed on the client machine so the client could find them easily. It could be an icon right on the desktop, or the help menu could actually open up this HTML document to allow the users to actually look at it. So this is the way I did it. I like having the documentation as much as possible, part of the project and part of the code, automatically built, automatically deployed on the client machine. Okay, so the positives, I would say, of that, document, we're embedded with code and projects, you define and update, generate both PDF and HTML, so you can use it online or you could print it out if you wanted, and automatically deploy to client. Negatives, I would say the documentation was somewhat incomplete, somewhat out of date, had a lot of mistakes in it, as opposed to every other piece of documentation you'll ever see about software, which is always correct and always complete and always up to date. That's not quite true, actually. Any document I ever looked at has always been out of date and incomplete. But overall, I think we did a pretty good job. I gave A- here. I think I might have even given an A on that one. I think that could be raised a little bit because I think the documentation at the end of the day was pretty good. And as much as everybody hates doing the documentation, it is an important part of the process and is absolutely necessary if you want to have a system that's going to be maintained. Okay, so I've now gone through about 5 or 6 different activities of the software engineering process, gave myself a grade. Okay, 2 test here is what is my final grade? Did I pass the course? Did I fail the course? So what's my final grade? Now, I decided what I would do here, get my final grade. I can do something simple, just take an average of all my grades. But why do something simple when you can do something complex? Okay, so I said, okay, problem with doing something simple is everybody understands what you're doing. Can't, they say in English, pull the wool over their eyes. So I said, okay, I'll do something a little more complex. The other thing I did while I was here is I started playing and learning all about Jupyter Notebooks. And I said, okay, well, here's a good chance to go into Jupyter Notebooks and actually do something productive and useful with Jupyter Notebooks. So, compute my final grade. Let's see if I can get all of this to work properly. Not what I see on my screen. Okay. Let me try something. Press goes down. Okay, here we go. Compute my final grade. So what I did in Jupyter Notebooks is first of all, I'm going to use Python computation to do this. I'm going to import a whole bunch of Python modules, probably have some experience with NumPy and matplotlib to draw nice pictures and graphs, SciPy. So I import all of those things so I can do a proper data analysis here. I then have to sort of somehow create a dict, that's a Python data structure of all my grades and its weights, which I do here. So I took my grades, and for each of those activities, I wanted to give a weight, because not all these activities have the same importance. So I did a Google search on the terminology relative to each of those activities, and the more hits I got on Google search, I figured that made that activity more important, and I gave it more of a weight. So I have my different weights here, and I create a dict that has the activities, the grades, and the weights. And of course, then what I have to do is I can't work with A's and B's and C's and F's, so I have to turn it into a number. And so I map A to 95 and B to 85, et cetera, et cetera. And then what I do is extract my grades and weights, and I said, what I want to do is get rid of the outliers. I don't want outliers to influence the results. So I take an average of my grades, and anything that's more than one standard deviation away from the mean, I discard. So I go through that, and you can see here, I create this grade filter here in NumPy, and I apply it to my grades. And when I do that, I can print out my grades, and amazingly enough, my F outlier, so I can throw it away. And then what I do is I take my grades and the weights of each of those grades, and I plot them on a graph. Not sure why, but it comes up with a nice, pretty graph as here. So down one side here, I got my grades, and there's the weights. And you look at that, and you say, that kind of starts looking like a normal distribution, sort of a Gaussian. So I decide what I'm going to do is try to curve fit that to a normal distribution. So I define a normal distribution with a peak of 100. That's the maximum grade. Then here I actually do a curve fit here, and I plot that out. Yeah, I got my normal, my bell curve there, and it's sort of more or less not bad, not a bad fit against my grades and my weights. Then to compute my final grade, I simply take the mean of my weights and put my curve fit function there at that mean, and that gives me my final grade. And now, unfortunately, I got to go back to the present. Find it here. Okay, my final grade, when I do the data analysis, A+. I passed. Not quite sure how that works, given that my highest mark was an A and lowest mark was an F, but you know, that's what the computer says, therefore it's got to be an A+. And anybody that believes that, I suggest you talk to your academic advisor about a course in statistics or data analytics or something. Okay, just some of the references I used to put together when I talked about the theory. There's a couple from Wikipedia, obviously, when I went to look at. I looked at a couple of IEEE documents. This was for architecture description, and I looked through their, called the SWBOC, Software Engineering Body of Knowledge. Pretty dry document, but gives pretty good definitions of a lot of the terminology. And a couple of the textbooks I looked through, Somerville and Pressman, that are two of the standard software engineering textbooks. And with that, I will call it a talk, and have Carol with a microphone. So if there's any questions, please feel free. Got one up here. I'm going to have to give the microphone because my ears are not as good as they were 40 years ago, and I have trouble understanding.
I just got confused on the part where you were explaining the GUI testing. I didn't get if you actually used a special like library or program, or did you write your own, or you wrote your own scripts in order to test the GUI? How did you manage to know where or when the GUI worked?
Okay, you said the UI?
GUI, yeah, the graphical user
Okay, the GUI.
interface, yeah.
How did we know it actually worked?
Yeah, because you explained that you use like scripts, but I don't know if you wrote those scripts or you used some, I don't know, from internet or something.
Okay, I'm trying to, no, we wrote that script. I'm trying to remember, that project was a number of years ago. I'm trying to remember how we actually got into the framework to drive it. I remember spending a lot of time researching tools to do this, and I couldn't find one that I liked that really worked. So we had to actually, and we didn't do it actually at the level of mouse clicks and mouse movements. I didn't try to simulate that. I had to go in at a lower level than that to make a function call to simulate the mouse click, but it wasn't really at the quote mouse click level. So yeah, we had to fake that a little bit. It wasn't really, we didn't have a mechanical arm moving a mouse and clicking, and we couldn't quite simulate that. So that I cheated a little bit there, but I think you have to cheat something like that.
Yeah. So the question that I have is that on the second one that you kind of evaluated yourself, you gave yourself a C, but I don't know, because I think that something that is a little bit complicated is to get involved with the users, because sometimes they can, as remember in your last talk, they can present resistance on the new system or something like that. So why would you consider that even when you got that connection with them, it was kind of like a C worth it?
It was kind of like, what was the last phrase?
C worth it. I mean, the worth of your work there was a C.
Well, as I say, my practitioner side disagrees with my teacher side. I think I deserve better than a C because I think we got the requirements correct pretty well on most of the projects I was working on. Yeah, you're right. I guess you were at my last talk when I talked about the user resistance. And that is always a difficult thing to overcome. But at the same time, even if you have a resistant user, you have to keep them involved, because you have to assume that they are going to be using the system eventually. And so it's important to keep not just the users that are anxious to use the system and really supportive, but the problem users as well. You have to keep everybody and all the users involved, because eventually those ones that are resisting have to be won over.
Right now we were working on a project in which most of the user complaints is that they don't have a manual that guides them. But
they don't have what?
A manual, like a user manual, yeah. And the problem is that they actually do, but they don't know how to access it. Like, this is like sort of like regarding documentation. Do you think like there's a common problem of developers assuming the user is gonna know how to access the documentation and understand it? Or should we strive to always like keep it simple?
Keeping it simple is always the right thing to do, obviously. Yeah, I mean, I sort of mentioned a lot of this documentation, the users don't know where it is or how to find it. I mean, I tried to make sure that the documentation got deployed along with the system, and that there'd be an icon on the front, right on the desktop that they could look at. And also on their menu, there's always a help menu on the end that when they brought that down, it could bring up that documentation. And because it got deployed every time the new system got deployed, the latest documentation was always available on their system. Yeah, you've got to think that through, how you're going to handle that situation.
Near the end, you mentioned that once you had your versions united, you deploy them to your users. But did you deploy them once you had all of them finished, no matter the time between deployments? Like, imagine if you had a week between deployments, did you really just send them? Because I imagine for users, it's kind of annoying to test this similar thing.
Most organizations have a release strategy. We did not, we normally do not release every time we had new features added to a system. We wouldn't add a new feature and deploy, add a new feature, deploy. We did not do that. That aggravates you because you get too many deployments. We generally wait until it was necessary for one of the features to be available to a user, and then we deploy. We didn't have sort of a release schedule. I mean, some organizations say every 6 months or once a year they're going to come out with a new release, or some companies it seems to be every couple of days. We didn't have a standard release schedule. We would release when we felt we had to release. And sometimes that would be fairly quick if we detected a problem or there was an important feature that was added. We might put it in and release right away, even if it was a short turnaround time. But sometimes we might wait a few weeks or a few months, even a couple of months or more, before we put out the release, save up, put a whole bunch of new features in and new bug fixes and everything. So yeah, you got to come up with a strategy for that, how you're going to handle your release schedule.
Would you say that's like some of the problems that Apple has? Like they're constantly releasing new iOS versions?
Yeah, I would say that.
And also, like, do you think like there should be like an ethical point to it? Because I remember like a few years ago, there was like this new news outlet that said that they were in big trouble because the new releases would often like mess up previous software.
Yeah, there's that almost at times that seems to be a strategy to mess up the previous stuff, to force people to upgrade and buy new versions. Yeah, I think a lot of organizations some of them are getting better at sort of coming up with a strategy of how and why to release. Tends to be sort of a lot of the younger and less mature organizations that are pushing out releases and aggravating users all the time. But I think most of the bigger companies, I think, have rationalized their release schedule to some extent.
I just have a simple question. What's the advantage of having like a computer or a script testing the GUI instead of an actual human? If humans are going to be the users that are going to test it instead of a script or a robot.
Okay, I didn't quite follow that.
Why did you create a script to test the GUI instead of having actual users test it?
Okay. Well, first of all, it takes users. You can test a lot more with a script over just having users test it. A script, you can just fire things at the GUI and sort of test things very, very quickly. Whereas users, they tend to have to, move the mouse, they click, and so you can test a lot more. You can do a lot of more regression testing. You have your standard tests, and you could have 1,000 tests, or thousands of tests, and just sort of build up your tests over time. And every time you see a new problem, add a new test. And so you can have, over time, build up thousands and thousands and thousands of tests and automate that. as opposed to trying to have a user, following a set of processes for each individual test. And if it's automated, it can take 3 days to run the tests, and that's not unusual. And you just start the test running and walk away and come back 3 days later and get your test report and see how things worked. Okay? Like it. Well, thank you very much. I quite enjoyed my time here, and I hope I can come back.